This is Dr. Fred DePiro, and this is a second video on mesh current analysis. This one has to do with handling current sources. After this, you'll be able to do a mesh analysis for circuits that include either voltage or current sources. And as with the prior video, another one of the learning objectives is to be able to relate mesh currents to the true current of a given element. Okay. Prereq is the ability to use the basic method of mesh analysis that just involves voltage sources. Okay, so as a quick review, why is mesh analysis useful? Great technique, powerhouse technique, handles arbitrarily large circuits, albeit they need to be planar. It's systematic, use the same procedure for any circuit, and the equations that are derived are via Kirchhoff's voltage law, easy. Okay? Guaranteed to be solvable. Going to yield n independent equations with n unknowns. And our unknowns are these mesh currents. Now, what are those mesh currents? Well, remember, they are theoretical constructs. They are defined to be each circulating around their own mesh. Here we have I1 defined to be clockwise and circulating strictly in the clockwise mesh. I2 in the left mesh. I2 strictly in the right mesh, as if the electrons were partitioned out into their respective meshes. Okay, this is an initial version of the technique that works for voltage sources only. We're going to define our mesh currents in the same direction. I'll choose clockwise. Then we have these options that are associated with Kirchhoff's voltage law. We can choose to apply KVL clockwise. We then must also follow passive sign convention to assign polarities for resistors, for example. We then must use the true currents with Ohm's law. And lastly, we have a choice as to whether we add or subtract terms in each KVL equation based on the plus minus polarities we might hit first going around the loop. Third step, solve the various KVL equations simultaneously. Okay, so that was a review. Now on to the matter of current sources. In some cases, they can require special attention. Reason is we don't know the voltage across a current source, and since we're using KVL, we need voltages. Now let's look at this case for a second. In this particular case, is the fact that we don't know the voltage across the current source, is that a problem in this case? Do we need to know the voltage across the current source in this case? How does the current source relate to the mesh currents? Okay, in this case, the mesh current I1 is determined by the current source. Okay, that's because mesh current I1 is defined to flow in a clockwise direction around this upper mesh. That includes this top piece here with this wire and the current source. Well, meanwhile, the current source is determining the current in that branch. Therefore, in this configuration, I1 is actually determined by the current source. Hence, that is not an unknown. The current source has eliminated that unknown and thus also eliminated the need for corresponding KVL equation, so we don't need to know the voltage across that. That's a good thing. Now, what about this case? Does the current source set the value for one of the mesh currents? It does not. Hence, in this case, we would need to know the voltage across the current source in order to introduce that into our KVL equations. Now that's kind of an interesting point. Now, so we need to include the voltage across the current source for our KVL equations. However, we don't know the voltage, so therefore what would we do? We need it, but we don't know it. Therefore, we define a new unknown. Yeah, that's a good idea. So we could use the unknown Vx, call it. It's a voltage, so we need to define not only the unknown quantity, but also its polarity. Okay, plus sign up, fine. And well, we just introduced another unknown, so now we're going to need to also introduce another equation in order to be able to solve. So what information is presented in this circuit that hasn't been used yet that we could then use to establish another equation? Well, the value of the current source itself hasn't been used. Now we'll need to incorporate that to form another equation that is related to the unknowns, which are the mesh currents. Okay, since the current source establishes a current, the mesh currents are also currents, it would be natural to consider using Kirchhoff's current law, since that relates currents. So what we could do is we could go to an intersection here, a T intersection here, a node that includes both the mesh currents in the meshes that are on this shared branch, as well as this wire coming up that includes the current from the current source itself. Okay, so consider doing KCL right at that node there. Okay. We can see that mesh current I1 is coming into that node from the left. Mesh current I2 is departing from the right. The current from the source is going up. So one formulation for KCL is innies equal outies. And we have I1 plus 16 equals I2. Sum of the currents into the node equals the sum of the currents out. Okay. So now we have this full version of mesh current analysis. First thing we'll do, as before, identify our unknown mesh currents. I'll choose clockwise to define mine. Then, if a current source is present on a shared branch, we need to define a voltage, say Vx, across it. Pick whatever polarity you want, but once you pick it, keep it the same. After all, Vx is an unknown, so we don't want to change the definition of our unknown, the polarity, for example, during the middle of the analysis. So pick the polarity, leave it set through the rest of the analysis, and then we can always use KCL to create another equation that relates the mesh currents, the unknown mesh currents, to that source current. Step 3 involves KVL. Easy now with that current source because we have voltage across it, so we can readily incorporate its voltage into the KVL equations, solve, and then of course an additional step, it's worth mentioning, if dependent sources are present, then we need to add another equation based on the definition of that dependent source. Okay, that concludes this video. So with some practice, hopefully you'll be able to do mesh analysis that includes either voltage sources or current sources, and importantly, to relate mesh currents to the true current of a given element.